So you're going to see just the heat effect expanding the oceans for a long time after you stabilise greenhouse gases. And the effect of ice sheet melting is even slower still. That's going to go on in this smooth view, neglecting any instabilities. This is going to take a long time, but that in the end you can expect a lot of melting from ice sheets. In the last interglacial, I think sea levels were 4 metres higher than they are now, for temperatures about maybe 3 degrees higher than they are now. But this, in terms of what's well established, is going to be a very slow process, and hopefully that is correct. But there is a risk that bits of it may happen faster. Again, typical cartoon of the carbon cycle, that you're talking about carbon in the atmosphere in terms of about, what are we up to about now, 800 billion tonnes. Carbon in land plants, and a lot of carbon in the ocean in various chemical forms, mainly bicarbonate. Rapidly exchanging between the atmosphere and the ocean is a natural process, with a small imbalance due to the fact that fossil fuel uses put the atmosphere out of balance with the ocean. Some of these processes are very fast. You can get carbon into the surface water within a year or so. Getting it down into the deep ocean is thousands of years. Land use change, putting extra carbon in, but the biggest contribution is from fossil. But it's the fact, the real killer on this is that what you're really doing is you are really mixing the carbon around. For methane, which is a greenhouse gas, the second most important of the human influenced ones, methane is broken down, it's destroyed, it's gone. That's the end of it. It's gone unless you put some more methane in. You won't be there. There won't be any there. With carbon, it's mixing back and forth between the atmosphere and the oceans. It never really goes away. All you can do, all that will happen, is a shift in location of where it is, which means effectively, in the long term, a lot will be in the ocean, but some will still be in the atmosphere. These are actual numbers that are probably a bit pushed for time. In terms of the natural exchanges, definitely for the oceans, having more in the atmosphere means that two-way exchange has increased, but that this is the human imbalance over this column here. And that leads to the concentration curves that David showed. A way I like to show this is by dividing it up into slices. What's the consequence of each 20-year chunk of emissions? You do this with a model, you run it with your carbon emissions, then you turn them off and you just see where the curve tracks, then you rerun it with turning them off 20 years later. So you can effectively assign each chunk of CO2 in the atmosphere to a 20-year band of emissions, or finer if you like, drawing lots of lines. What it's saying is that some of the older stuff is effectively there for a very long time, and that any room you have to play with in terms of cutting concentrations, you really only have this little bit of area above, that some group people have called headspace, to define how much extra CO2 you can put into the atmosphere. The effect's even more pronounced in terms of warming, from the committed warming effect, that you even get this, it's very hard to see here, if you stopped emissions, you would actually, under these calculations, get a very slight initial increase in temperature, even though the CO2 is dropping, and that the tail off, even with no emissions, is very, very slow. Again, you have little room to play with in terms of controlling things. The actual calculations, very simple. You normally run a model, those IPCC results, you calculate, you know what the sources are from your scenarios, you calculate the losses, change of concentration is therefore the difference. If you're deducing sources, you just turn that round, you're calculating losses, add the change of target, and that lets you know how much you have for your required sources. So these are some new numbers. They show a little more detail than what the IPCC showed. This was for stabilising CO2 at 550, and in the planning, of course, David reminded me of the important point that this is for CO2 only. To stabilise climate, you also need to have some stabilisation of the others. They will add to any CO2 warming, and it was only the CO2 part that I actually plotted on the previous curve. You have a bunch of choices as to how long you let things go, but the longer you go without any action, the faster you have to reduce thereafter for any particular stabilisation level. This was a range of possibilities of what you could achieve from 1995. Since this didn't happen, this is from 2005 notionally. I should have probably done the 2010 set. You now have a lot fewer choices. You're now locked into, for stabilising at 550, you're locked into the cases which have the faster rate of reductions later on. This is even more dramatic if you say you want to stabilise at 450 and then allow a little bit for some methane in terms of the total forcing. Back in 1995, there was still a range of cases. There's rather little you can do in terms of smoothly changing emissions from now on, that anything you do from now on is going to get steeper and steeper. How about a couple minutes? The national targets, those numbers were how much the world as a whole needs to reduce CO2 emissions to stabilise concentrations. For national targets, you then have to say, okay, how are you going to assign these to individual nations? The Kyoto Protocol is, of course, a very crude first step in getting an agreement. It isn't a framework that's sustainable in the long term. Two fairly widely proposed, one a contraction and convergence where everyone is converging towards equal per capita emissions, which is going to imply a much greater proportional reduction for developed nations. And perhaps even more dramatic, the Brazilian proposal that actually had the idea that everyone's reduction target should be in proportion to how much they are to blame for the warming we've had now or at some particular time. And that's actually formally on the table in negotiations. It'll be formally considered at this substantive working group this year and at the climate change conference of parties in the middle of next year. And I probably haven't got time to say a lot about feedbacks. David mentioned the concept that this is the climate carbon one. It's where the big unknown is. It's where the interesting science is, and a lot of that band I showed before. This is the cartoon that we normally were talking about carbon dioxide influencing warming, but there is an effect going back the other way. We actually see this. Some of the things that David showed, this slight northern hemisphere cooling corresponds to a slight cooling in drop in CO2. And this is that feedback part of the cycle. The change in CO2 is too small to have caused cooling, and the cooling may well not have been global, but there is a CO2 dip. It's that other half of the cycle. You're seeing something a little bit similar in the 20th century, CO2 flattening off, at least the early part of the cooling. Later on, of course, industrial emissions post-World War II totally swamped that effect. And in the glacial interglacial one, David mentioned this, that CO2 is an important part of driving the ice ages. What I've done is replot these in proportion so that the temperature scale is they're all in proportion to how much warming you would expect from the CO2. And so the glacial one has been scaled back to what a global average would be, because the polars tend to have a larger signal. Methane turns out to be a very minor player in causing things. It's more being driven by the climate change when you actually track through the numbers. But this would suggest that CO2 is responsible for about half the warming, amplifying the signal from astronomical variations that David talked about, but that is a very important part in causing those variations. Okay, thank you.